All right, we are going to go over the linear motion notes. We're going to get into kinematics now, and we are going to talk about 5 different concepts. The first one being position, and then we're going to look at distance versus displacement, and then we're going to look at speed versus velocity. So let's start off talking about position. So position is a pretty simple concept. Something is located somewhere, and we can identify where it's located based on our Cartesian coordinate system. So I can say this is located here relative to me. And so when we talk about position, there are several different letters that can identify a position. We can use D. Sometimes S is used. Sometimes X is used. If we're talking about a vertical position, Y might be used. So it's sort of confusing, and I'm sorry about that. I did not invent the system. I tend to use X when I'm talking about position, but all of these things can be used, just so you know. Okay. And then when we talk about distance, so distance is a scalar, meaning we're just talking about the magnitude, 5 feet, 8 meters, what have you, away. And so we're talking about how far something has traveled without talking about which direction it's from us. Okay. And so that is different from what we call displacement, which is a vector, because when we talk about displacement, we're going to say a direction as well. It is 8 meters east. It is 20 feet to the north, or what have you. So for example, we look at this fly. And so this fly is going to get a bite of this burger, and it's zooming around in this circuitous path to get here. So if the burger is, say, 6 meters away, the fly, because it didn't travel in a straight line, traveled more than 6 meters. So the distance would keep on adding up. If it does like a circle and whatever, it is going to keep on adding up. It just is going to keep on moving along until it gets there. And so the total distance will be whatever this path adds up to be. That's different from displacement in that if the fly flies along this path, it only went from point A to point B, and that's its displacement, the shortest distance between 2 points, okay? It started here and it ended here. That's all we care about, and that is 6 meters. But it is 6 meters with the direction, and that direction is, say, in this case, to the right. And to the right is going to be a positive direction in the X direction. So we could also indicate it as a plus 6 meters. Okay, so you can look at the speaker notes down here and get a more complex definition if you need. So then we're going to come over and look at this baby, which is crawling. And so the baby starts here. It's going to crawl along for 6 feet, and then it's going to make a nice 90-degree turn and go straight up for another 3 feet. So what distance did the baby crawl? Well, you just add it up. 6 plus 3 is 9 feet. What is the magnitude and direction of the baby's displacement? Well, now we're going to say that this red line is the displacement, and that is our hypotenuse of this right triangle. So we can use Pythagorean theorem, say 6 squared plus 3 squared, take the square root of that, and we will come up with 6.7 feet. Okay, so this distance is 6.7 feet, and that is the displacement of the baby because that is the shortest distance between those 2 points. Now, the other thing I have to add is the direction. So the baby was crawling to the right, and then it went up from that. So you can say it traveled 6.7 feet. You could say it traveled 6.7 feet left of the original path. So this was the original path, and it traveled 6.7 feet and to the left of that path. So that's going to bring us into speed. And speed is something we talk about all the time. I was driving in my car and I was going 20 miles per hour. So speed, the S, is a scalar. We're just talking about the magnitude. So it's easy to remember that speed is a scalar because S for speed, S for scalar. So when we're driving in our car, we look at our speedometer and it tells us how fast we're going. It doesn't tell us what direction we're going, and the odometer will keep on ticking. So think about that. Is the odometer measuring displacement or distance? The answer is it's measuring distance, because it's just going to keep on adding up. It's not going to record the shortest distance between 2 points. So we're talking about speed because we're talking about distance, and I'll get to that in a second. So as we're driving, you will see this move up and down. That is going to tell you, the speedometer will give you your instantaneous speed, your speed at any given time. The average speed is going to be equal to the total distance divided by your change in time. Okay, so to get the average speed, you just take whatever distance you traveled and divide it by your change in time. So then we're going to talk about velocity. Now, velocity is going to involve displacement. So velocity is a change in an object's position, which is displacement, divided by a change in time. So velocity is a speed in a given direction. So we're adding that direction to take it from speed to velocity. And velocity, v, is a vector v. So once again, it's pretty easy to remember that. Okay. So here is our velocity. So velocity is equal to displacement divided by time. This question here, can you maintain constant speed yet have a changing velocity? And so think about that. If you're driving along in your car, if you don't touch the accelerator or the brake and your speedometer is reading the same number, can you change your velocity? The answer is yes, you can. All you have to do is turn your steering wheel, because a change in direction is going to give you a change in velocity. Your speed might remain the same, but your velocity will be different because your direction has changed. Okay, so this formula here, delta D, your change in displacement, is equal to your U here is your initial velocity times time, plus 1/2 the acceleration times time squared. We'll get to this formula later on. For now, you just are being exposed to it. Okay, so then we're going to talk about a velocity example, or a speed and velocity example. So this baby now, that from the other example, is crawling along. It goes 6 feet this way and then 3 feet this way. So what speed did the baby crawl? So for speed, we're going to look at distance. The distance it traveled is 6 feet and then 3 feet, so a total of 9 feet, divided by the time it took, which was 20 seconds. So to get the speed, I'm just going to do the total distance, 9 feet, divided by 20 seconds. And if I do that, I come out with 0.45 feet per second. Okay. What is the magnitude and direction of the baby's velocity? So now for velocity, once again, we're going to talk about displacement. So the displacement here was 6.7 meters, or feet, sorry, 6.7 feet. And the time was 20 seconds. So 6.7 divided by 20 is going to give us 0.34 feet per second. And again, to the left of the original path. So we have to give the numerical value, the magnitude of the speed, in this case, 0.34 feet per second, and then also the direction to make it a velocity, and that is to the left of the path. Velocity here, and we're going to look at this graph. And so when we look at this graph, we see distance on the y-axis and time on the x-axis. And this is uniform velocity. So the same units or same distance per unit time is being traveled. It is constant, uniform. And so this is a distance versus time graph. And the important thing about a distance versus time graph is when you look at the slope of the distance versus time graph, if I were to do rise over run, distance over time, you can see that my units will be meters divided by time, which would be in seconds, so meters per second. That is going to give us our velocity, or our speed. So it is important to know that velocity is the slope of a distance versus time graph. Okay, so now we're going to look at a position versus time graph. And so the position versus time graph, we have D on the side here on the y-axis, and then t on the x-axis. And it's important to see here that when we start here at our origin, we're starting at 0, that the position is changing over time, okay? And so here, this person or object is moving away, and it gets to 60 meters away in 10 seconds. So using the equation that our final distance, 60 meters, minus our initial distance of 0 meters, divided by that time interval of 10 seconds, would give us that this person, let's say they were walking or running in this case, traveled 6 meters per second. And it is a positive 6 meters per second. Okay, so that's the first part of this. Then the important thing to see here is that in the time interval 2 here, you can see that position is not changing. If position is not changing, then velocity is 0. So the change in position is 0. 0 divided by the time is going to give you 0. So there is no velocity here. Okay, it's 0. And then going from here to here, you can see that there's going to be a negative velocity. Okay, so because it is coming towards, it is going to be a negative velocity. And so we're going to look at the final position of negative 40. We're going to look at the initial position of 60. We're going to say negative 40 minus 60 is going to be negative 100. And then the change in time is going to be 40 minus 15. So 100 minus, what's that, 25 is going to give us our velocity of negative 4 meters per second. Okay, so a negative velocity indicating that the person is coming back towards the initial position. Okay. Going to be a little bit confusing and maybe scary to people at first when we talk about taking the derivative. So for this question here, what is the car's instantaneous velocity at 1.2 hours? So we like to talk in physics a lot about uniform motion and constant velocities and things like that. So when it's not constant, how do we know what the instantaneous velocity is on this distance versus time graph? So to do that, all we're going to do is draw a tangential line and then use that tangential line and calculate the slope of it, and that will give us what our instantaneous velocity is at that point. So that's worked out for you right here, that you just draw a line tangent to the slope and then use that line to calculate the slope at that point, and that will give you the instantaneous velocity of that graph. All right, and so for this last one, displacement is the integral of a velocity versus time graph. And so once again, we're not going to use calculus in this class, but if you know your calculus, you could take the integral of this and you could figure out what the distance traveled or the displacement of the dune buggy was. Another way of thinking about that is the integral is the area under the curve. And so if we were to count all the boxes under here, that would tell us the displacement of the dune buggy. So again, the other way to kind of think of it, the integral is going to be your velocity times your time, and that's going to give you an answer in meters. So there's two ways to go about solving this one. One, I can kind of look at this right here and say, well, that right there is a right triangle. And so if I look at that as a right triangle, I can use 1/2 base times height to determine what the area under this part of the curve is, so to speak. And then I can say, well, this right here is a rectangle. And so I can use length times height to get my area there. And then once again, over here, I have a right triangle and I can determine the area there. Now, what is the average velocity here? So between this point and this point, I go from 0 to 2 meters per second. And that happens over a period of 2 seconds. So on average, the velocity was 1 meter per second. 1 meter per second for 2 seconds. During this time, 2 meters were traveled. From here to here, it's pretty easy to get the average velocity. The average velocity was 2 meters per second, and it was 2 meters per second between 2 and 6 seconds. So 4 seconds at 2 meters per second would give me 8 meters. So I have 2 meters, 8 meters. And over here, I go from 2 to 0. So that is going to give me an average of 1 meter per second again. And that 1 meter per second for 2 seconds. So that's going to be another 2 meters there. So I could say 2 plus 8 plus 2, and that's going to give me 12 meters. And you can see that if you do the area under the curve, you will also get 2, 8, and 2 for a total of 12 meters. That's going to be it for the notes for today. Have a wonderful rest of your